3:30, 4 o'clock. Fine. So today we'll see one of the new topic you may not be knowing about this, like hydrogels. It's a kind of one of the substrate or the morphology where people use specifically in the biomedical applications. Kind of tissue regeneration as well as for the contact lens as well as for biosensor and drug delivery applications. Then what is hydrogel? So this is how the hydrogel looks like this. They kind of looks like jelly-based structures, or you can say like a swollen polymeric structures. That's what hydrogels are water swollen and cross-linked polymeric structure, and it's produced by the simple reaction of one or more monomers or association of bonds such as hydrogen bond. There may be a strong van der Waals cross interactions between the chains. Okay, so they take a protein or the polymer and then they dissolve it in the water, and due to that tendency for the formation of hydrogel structure, that means three-dimensional structure, with the help of those secondary bonding like hydrogen bond or van der Waals interactions. Okay, so with the help of that, the water molecule will be associated with the polymeric structures. So once the hydrogel is formed, that means it is water insoluble, and it's a three-dimensional network structure by the bonding like a chemical or physical bonding. Physical bonding means like hydrogen bond and van der Waals, and if it is a chemical bond, then again there will be interactions of third moieties, maybe of some inorganic filler or some sort of another kind of curing agent. Okay, and like polymers capable of swelling substantially in the aqueous media. That means your polymer should be in hydrophilic nature. Okay, and polymeric network in which water is dispersed through the structures. Okay? So, sorry, yeah. So the cross-link can be a physical and chemical. Okay, and of course you may be knowing physical cross-linking means you can easily dissociate those bonds. With the help of simple heating or with the help of any simple simulating the mechanical stress, etc. Either if it is chemical cross-linking means and since the bonding is very strong, you cannot disturb the bond simply as that of physical bonding. So you'll have to produce either more heat or some sort of irradiation, something like IR or UV or kind of some blue light, etc. If you want to dissociate that bond. Okay. So we'll see why to disturb the bond. Either physical bond or chemical bond. So chemical crossing again. Yeah.
So are you sharing a PPT?
Oh my God. Okay, I didn't do that sharing option. Huh?
No, sir, I don't think so.
It's visible, sir. It's visible.
It's visible,
Oh,
right? No,
okay.
no, it's sharing mode only. Correct.
Yes, sir, it's visible. Sir.
I'll join back and check. Maybe something issue.
Yeah, maybe you have some issue. Check it.
Yeah, I'll just join back. Sir. Yeah.
Okay. So I thought that I didn't even start the screen sharing, and I started my presentation. Fine. So chemical costing again, like a kind of chemically cross-linked. That means absorb water until there is equilibrium swelling. They are cross-link dependent as well, and they are highly stable. Of course, as I told you, that chemical cross-link is pretty high. Bond strength is pretty high. As a result, they can withstand in any kind of harsh environment, like high temperature, acid basic condition, even if you apply very high strength, high stress kind of mechanical load, they withstand. The bond will not break. As a result, your stability will be enhanced. Okay. Again, physical cross-linking just opposite to that. Since they are very weaker, and even with the help of small forces, you can disturb their bonding between that chains. Okay. Well, the formation mechanism usually, if it is physical cross-linking, of course, that should be the electronegativity differences in the charges. Then only the hydrogen bond will form or the van der Waals interaction would happen. So one or more highly electronegative atoms used to participate for the formation of these secondary bonding interactions, which resulted in charge asymmetry favoring a hydrogen bonding with the water or any other organic medium. Because of their hydrophilic nature, dry materials usually absorb more water. Okay? And if the hydrogel absorb, it should absorb minimum 10%, then it can be considered as hydrogel. And if it is exceeding more than 95%, if the polymer is, the monomer or the polymer, if they are absorbing more amount of water than more than 95%, means that is super absorbed. So a few, this one definition like chemically processing hydrogel means like they form network structures, and it can be like kind of reversible structures. That means kind of shape memory properties. And since the properties are unique of the gel, the ability to maintain the original shape even after swelling as much as they do. Okay. Yeah. As I told you that once the hydrogel is formed, that means that once the three-dimensional network is formed, it cannot be reformed. No, it cannot be dissolvable at all. Okay, means if you put it in any solvent or any kind of organic media, they will not dissolve at all. Also, there's no flow even if in the steady state conditions. Okay, and by weight, gels are mostly liquid, yet they behave like a solids. Okay, and they can absorb, large quantities of water. Even they can go up to 1,000 times from their dry. Okay. And these are the few differences, like chemically crossing to one and physically crossing to network structures. And usually, like chemically crossing means usually we used to call thermoset hydrogels, and if this is physically crossing to network means they are thermoplastic hydrogels. Okay? And since the bonding is pretty strong in chemically crossing hydrogel, the reliable shape stability as well as the shape memory properties. But of course, in case of physical hydrogels, you can't rely. The stability as well as the shape memory. The shape requirements will be pretty much less as compared to the chemically crossing. So this is simple. Reaction scheme for the preparation of hydrogel. So you're gonna take a monomer, and then the monomers will be dissolved in the water. And if you need kind of chemical cross-linking, then you will have to add some cross-linker, and the polymerization continues. And at the end, you will have this kind of network structure polymer which has water inside that. Okay. So these are the few structures of polymers and the cross-linking units. Say for example, you can see here. You have an electronegativity group, OH groups here, and you have a, proton groups here, NH damping groups. So plus or minus, there is a differences in the electronegativity charges, and as a result, the formation of hydrogen bond is pretty, easier. So this was, network structure which was formed after gelatin with rextranol-based and this one again another one example with the gelatin and then gelatin methyl-acrylamide based solutions. Okay? And so these are the few polymers like natural and synthetic polymers where the hydrogel can be prepared. So if you want to prepare the hydrogel, first of all the polymer should dissolve in water actually. Then only the polymer can be prepared for hydrogel. Okay? So again, now like when you'll come to know that your hydrogel is formed. Okay, one thing is that once the polymerization is done or once the preparation is done, the viscosity will increase actually, and that you can have a look by your knack, right? Or you can go ahead with some scientific experiment by measuring the viscosity or some mechanical properties like elastic modulus or the loss modulus or the tangent. Okay. So kind of rheology, you can study the flow behavior of the hydrogels. Okay. So here you can see here, we have two different biopolymers. One is R-lactate and L-lactate, which has a different entanglement, amorphous core and crystalline. And one of the papers like so other like Khalid et al. Biomedical 2003. They have prepared this I mean, hydrogens with the help of two different, this one polymers, which has a different molecular weight as well. So you can see here, with the increasing the molecular weight, again the formation of hydrogen, I mean the viscosity or the elastic modulus is also increasing. And if it is crystalline one, I mean even the viscosity is pretty much, I mean, high. Okay? And of course, in case of this amorphous core, the cross-linking network, once, with the increasing of the frequency and the vibration, you can see how the elastic modulus is increasing. That means again, that there is some kind of cross-linking is happening with the help of this mechanical simulation. Okay. Again, another one example where you can see with the help of nanoparticles like clay nanoplates, we add clay nanoplates into that hydrogel, kind of polymeric hydrogel, how whether the hydrogen bond is forming or not, or if the hydrogen bond is forming, whether it is helping for improving the mechanical properties of the hydrogel or not. You can see here, once they started to add this nanoplatelet, like a laponite based nano disc actually, you can see here the increases in the elastic modulus as compared to that of pristine sample polyethylene oxide based hydrogen. That means because if you see the clay nanoclay, which has surface function, OH functionality is there, which is electronegative groups, and they actively participated. Participate for the formation of hydrogen bond within that interaction. The mixing. So these are the few characterization tools that can use this tools for finding out that your hydrogel has been formed up. Okay. Yeah, these are the few applications where I was telling, like a drug delivery, tissue regeneration, scaffolds, and product analysis as well as cell killing. Fine. So now we'll see one of the example, like how the hydrogels are used for drug delivery. Okay. Again, here also we have like two different types of drug encapsulation or the loadings. Okay. One is physical loading and another one is chemical loading. That means you are preparing the hydrogel three-dimensional network, and into the structure you are adding drugs into that. Okay. Physically loading. That means with the help of secondary bonding. And once you are loaded the drug physically, you can release it. Like the same, and maybe you can change the pH or the temperature, or you can do other some simulating some environment, like introducing some electrical energy or some magnetic environment, etc. Once you do that, the physical bonding will be disturbed. As a result, the drugs will start to come out. Okay. And in case of chemical drug loading, means you are attaching this drug chemically into the main chain of the polymer chain, like water. Okay. As a result, the main drug and the main carbon chain will be linked by this cross-linker. Okay. And if you want to release the drug, you have to dissociate this enzyme-based bond. You have to clean, break those bonds. That can be done either by using kind of several IR or some sort of UV ray, etc. Okay. Or you can use some laser light as well, or some enzyme-based cleavable agent as well. So once you do that, the drug will start to release. This is one of the drug widely they use for biomedical applications. So now, question is that we have a different substrate. Like you can see, we have films, and then we have fibers, and then we have kind of some spherical based gel or micellar basic structures, and then we have 3D printed structures, and then we have a hydrogels. Okay. So the drugs can be encapsulated in any kind of substrate, but of course, how much the drugs is encapsulated into the specific substrate, that is more important. In case of fillings, you cannot incorporate drug as much as, but in case of fibers, you can incorporate slightly better or slightly more than that of fillings. And it's keep on increasing. When it compares to the hydrogel, you can incorporate the drug as much as you want because you have a 3-dimensional structure and you have a more randomness presence in it. So maybe I stop here. Your exams will be till the hydrogel, not the application part. But yeah, because we'll have to read more about these applications. So before that, I'll have to teach what is 3D bioprinting and what is micellary gel or vesicle structures. Then I can able to then you'll be knowing the comparisons why hydrogel has more drug encapsulation or more drug loading capacity, etc. It's a pretty continuous for a long time. So I stop here. How many guys are used? 5. So if we want to shift this class, where we can do? How? You're not taking this one, right? FFC, Foundry Technology. No, what is this one? Sorry, here. Oh no.
So that's for a junior, sir.
Okay, yeah, that's for 5th semester, right? Okay. Okay, no, we cannot pre-bond it, but we can post bond to like 415. Huh? Can keep it here. I don't have to wait for you guys and fine. So I'll inform Anand and I'm informing you guys also. Like from Friday, next Friday onwards, we'll meet up at 4:15. Okay. Sorry. Yeah.
Yes, sir.
All right. Yeah. Okay. And anything else? Still hydrogen the basics. You keep it for your exam next semester. And it will be a combination of MCQ and descriptive format and then interpretation of some of the results from the paper. I'm not going to ask you to read all the papers, pages. I'll pick up some of the images and then I'll ask you the questions. Huh? Okay.
Okay,
See
sir.
you then. Bye. Yeah.
Thank you, sir.